all the volume we've done so far has to do with rotating around a line. Today what we're looking at has nothing to do with rotation. These are solid objects that are already solid objects. We're not creating them by rotating. What we do know about these objects is that they have known cross sections, and we'll explain what that means in just a second. So here's what I want you to do. I want you to look at this graph over here. Okay, the graph of the circle. Now what I want you to think about is imagine that you have a cylinder, like a tennis ball case, something like that, tennis ball canister. So you have a cylinder and you place the bottom of the cylinder on your computer screen, or however you're watching this. So you could trace the bottom of that and it would make a circle. So what we're seeing is just the base of a shape, in this case a cylinder. But a cylinder is coming out of the board. Now if we were to take thin slices of that cylinder in the direction of those red lines, it would create rectangles. Okay, now we could also, say, take an ice cream cone, turn it upside down and put the opening of it against the board or the screen you're looking at, and then coming out at you would be a cone. Now it's got the same circle as its base, so we'd have the same thing on the board even though there's a different shape. Now if you take slices out of the cone, it's going to give you triangles. Or lastly, if you think about like cutting a Nerf ball in half and then putting the cut part on the board, you would have a hemisphere coming out at you. And in that case, if you were to take thin slices of that, it would create a semicircle. So you notice different shapes can all have the same base, and they can have therefore different cross sections when you're cutting or taking thin slices out of that shape. So the formula for the volume of solids with known cross sections is this right here. And it's just the integral of the area function. And the area function is just the area for the cross section. So before we had base times height, excuse me, I got ahead of myself. When we did the rectangles, if you cut cylinders in little pieces, it would be rectangles. That would be base times height. The triangles is half times base times height. Semicircle would be 1/2 pi r squared. So let's start with an example. Okay, so let's say we have the base of a solid that's formed by the region bounded by y equals 1 minus x over 2 and y equals negative 1 plus x over 2 and x equals 0. So let me show you what that looks like. It's this picture down here in the green and blue. And it says that its cross sections are squares. So I use this formula right here, because the integral of side squared, that's the area of a square at side squared. So the next thing I need to do is figure out my boundaries. Well, they gave us one boundary, x equals 0, you see that right here. And to find the other boundary, we set the two of them equal to each other and solve, and we get 2 equals x. So that's how I got the integral from 0 to 2. Now, to get the length of my side, just think about that red line. So what you can't see is coming out of the board is a square, and this is just the base of it. Okay, so just imagine taking a sheet of paper and putting one side of it right here. It'd have to be a square sheet of paper, but still. So there's coming out of the board a square, where this is one side. So the length of that side is just the distance from the top equation to the bottom equation. So I do the top equation minus the bottom equation. That's my side squared. And if you plug that in, you get 8/3. Okay, now we're going to use this same base for several different shapes. So next, let's assume that the cross sections are rectangles with a height of 3. So in other words, when you come out of the board, you know this is a rectangle and the height is always 3 no matter where you come from. Now it's important, if you think back to when we had it as squares, this shape was going to be bigger here because its height would be the same as its base here than it is here. So this is almost going to look like a piece of pie, when it was squares that is. It was going to look like a piece of pie that was really thick at its crust, but then as you move down towards the tip, it became almost no height at all. It became very thin. Now with rectangles, so it's going to be the same height every time. So this is more like a wedge of cheese. It's got the same height all the way through. So the formula for a rectangle is base times height, which is what I have right here. But they tell us that the height is 3, so I replace h with 3. So I need to do the integral of 3 times the base. So I put 3 out front, And the base is going to be that red line again, so I just do top minus bottom. So hopefully you see this is really simple. It's very similar no matter what shape you have. So let's keep going. Let's say we have cross sections that are rectangles whose height is 5 times their base. Okay, so we have base times height, that's the area of a rectangle. Now they tell us the height is 5 times the base, so I replace the height with 5b. If you simplify that, it's 5b squared. So I put the 5 out front, and I do top minus bottom, because that'll give me the base, squared. Now if you look, that's actually the same as the one we had up here, except we're multiplying by 5. So I just took this answer 8/3 multiplied by 5 and it got me 40/3. Okay, let's say there are cross sections who are equilateral triangles. You can use trig and figure out this area formula if you want. Basically with trig what you find out, if you watch what's in blue over here to the right, that you can relate the height to the base. The height is always going to be square root of 3 over 4 times the base. So when you simplify, you get this up here. So this is our equation for equilateral triangles. So I put square root of 3 over 4 out front, do top minus bottom to get my base, and I square it. You get 1.155. Okay, now this next one is tricky, so I need you to think carefully with me. It says the cross sections are semicircles. Semicircles. Okay, the key here, you know the area is 1/2 pi r squared, but so far every time we've needed a distance, a base or a height or a side, we've just done top minus bottom. But I want you to look over here at this picture with me. Okay, if you think of this red line as the base, and then you've got a semicircle coming out of the board, that red line is not the radius. And our formula is pi r squared, 1/2 pi r squared. So that's the diameter and we need the radius. So that's why over here, in front of the top minus bottom, I have a 1/2. Because I need to do top minus bottom, which is my diameter, times 1/2, which is my radius. So you've got to multiply by 1/2. Now if you notice my parentheses have the squared, including it squaring the 1/2, because you want to make sure you have the radius first. So you do top minus bottom, that's the diameter, times 1/2, that's the radius, then you square it. So these parentheses can get really sticky, and you've got to be very, very careful. One thing that may help if you want, if you can remember this, if you think about it this way, this 1/2 is going to get squared, which is why I wrote 1/4 down here. Then if you pull that 1/4 out front and multiply by the 1/2, you're going to get 1/8. So one way you can do semicircles is still just do top minus bottom over here, but you're going to have to pull a 1/8 over here. Again, that's because you got to cut it in half, square that, that's 1/4, times the 1/2 that's already out front because it's a semicircle, and you get 1/8. But if you plug this one in, you should get pi over 3.